Hello, everyone. This is Kenan, and I'm a PhD student at Izmir Democracy University. In here, I'm recording the work, which is still in progress, that we've done regarding classification of COVID-19 images. The work is titled Automated Classification Algorithm Attempts for COVID-19 and Non-COVID-19 Diagnosis, mainly called COV-19D, with an international competition. And then in here, I'm going to be presenting two case studies. And with those two case studies were in a team, which included me, Taha, and Associate Professor Devri Monai. Let's go ahead. Okay, so what is the contents? I'm going to be presenting an introduction and the aim of the project, the dataset which was used, the pre-processing of the dataset, the methodologies. Actually, there are two case studies, so there are two methodologies used in here. The results on both of the case studies, further work, and there's great emphasis on the further work as it's continuous, acknowledgement and references. Let's go ahead. Introduction and the aim of the study. So the work here aims to develop an automated classification algorithm for COVID-19 and non-COVID-19 diagnosis. The project includes working on a chest CT scan series of images. A database of the CT scan series that is manually annotated with respect to COVID-19 and non-COVID-19 diagnosis. So the manual annotation was with respect to being to a binary classification work, which is either COVID-19 or non-COVID-19 work. The ultimate aim of the project is to reach a high macro F1 score. So what we aim in here for this project is mainly to get a high macro F1 score, right? The baseline score or the base results on the validation set is 0.70. So basically, it's very much preferred to reach higher than the 0.7. Okay. The paper here shows a convolution neural network module and also a transfer learning module. So these are the two case studies. One is concerned with a convolution neural network, and the other one is concerned with a transfer learning module for feature extraction and then a simple classifier. Both of the methods aimed at increasing the macro F1 score for the task of image classification for COVID and non-COVID diagnosis. The first case study module was a convolution neural network build module with 5 layers, and I'll get to that later. The second case study was following transfer learning methods of feature extraction, and that was followed by a classifier to finish up the final task. Both of the modules showed moderate results in terms of the macro F1 score, which is the ultimate aim of the work. Perfect. So let's discuss the dataset. The source of the dataset is called COVID-19 CT database. It's again manually annotated for the existence of COVID-19 in chest CT scans. The COVID-19 CT database consists of about 5,000 chest CT scan series, which corresponds to a high number of patients, more than 1,000 patients. So these scan images taken from more than 1,000 patients. The training sets contains in total 1,560 3D CT scans, and these include 690 COVID-19 cases and 870 non-COVID-19 cases. The validation data set, on the other hand, consists of 374 3D CT scan images. 165 of them represent COVID-19 cases, 209 represent non-COVID-19 cases. Now, both of the data sets include different numbers of CT slices, right? So you get the 3D images, and then you want to do slicing to them. For each image, you can find from 50 to 700 slices. And the initial images are all provided in a JPEG format, JPG format. These are for sure the references where the work, where the images and previous work was done in that area. Okay, perfect. That's about the data set. Now, pre-processing the data set. First, extracting the files, RAR files which had to be extracted, and then removing any hidden interrupting paths in the images. And then in Python, data image generator was used to build a flow from directory. So the images were created with a rescaling, basically. So it was divided by 255. Further augmentation can be implemented through a data image generator. The images then were flown from directory with labels and other specifications which were passed to the images. Those specifications will be different between the two case studies. For the convolution neural network module, the first case study, the images were passed in 3 channels, for example. For the transfer learning, however, the second case study, the images were converted to grayscale and then was passed to a 1-channel feature extracting VGG transfer learning module. Images in the first case study were kept of 512 by 512 size, whereas in the second case study, the images were resized to 128 by 128 so that it's less computationally expensive. Okay, that's pre-processing the data. Let's discuss the methodologies. The first case study, so a CNN module was sequentially arranged in 5 layers. You can also see the 5 layers on the right hand of this presentation. The input images, the input function takes 3 channeled images of size 512 by 512. The layers all use a 2D convolutional layers along with max pooling of 2 by 2. And a dropout function was also used in the last 4 layers. Only in the last 4 layers, not the first one. The 2% is the dropout. Flatten and 2 dense layers were used finally in the last layer, right? So flatten and 2 dense layers were used in the end with a binary output. The activation function was reU for all the layers except for the final results. It's a sigmoid activation function at the final dense layer, right? The sigmoid function, give it a binary work. The optimizer used in here was Atom optimizer with all its default values on Python and Keras. The module was trained using loss function to be the macro F1 score. So it's about maximizing or optimizing the macro F1 score function. That's the loss function used for in case study 1 while training the module. Okay, so you can also get to see the GitHub, the link down there to see how this how the code was written for the first case study. Perfect. Now, second case study, or second methodology, transfer learning paced second case study was applied only on 30 CT images for the training and 30 CT images for the validation. So out of all the images that we received, only 30 CT images were taken from the training set, and 30 CT images were taken also from the validation set. So the number of data or the number of images were way less in the second case study to avoid computational expensity. The original images modules was changed to grayscale as well and resized to 128 by 128 images, right? Smaller sizes of images. The training images were used in the VGG16 transfer learning module to extract features, and no further training was done on this transfer learning module, right? So all the parameters were untrained. Only the features were just simply extracted, and the input images were only 1-channeled images for this transfer learning module for the VGG16. Now, the extracted features were then used to classify the images in the validation set using random forest, right? So the classifier used in here is the random forest classifiers. The parameters for the random forest classifier were pretty much random or arbitrary. It was the number of estimators were chosen to be 50, and the random state was chosen to be 42. The emphasis was not very much put on the classifier per se, because it's not going to give the better results, or it won't change much when you change the classifier. Rather, what you focus on is the transfer learning method itself, which could change the final results. Okay, perfect. And then you can get also to the link down there on a GitHub to access or to see the written code in there for the second case study. All right, let's discuss the results now. The results for the case study 1. Again, the focus is on the macro F1 score. So the macro F1 score in the first case study averaged around 0.7 over 200 epochs. So the module, the CNN module, was run over 200 epochs, and the macro F1 score was always kept at 0.7. So that's the average F1 score. The step per epoch for both the training and the validation sets were equal to the length of the created generator divided by the training generator divided by the batch size. So this is how the step per epoch during the training was taken, right? So it's the length of the training generator divided by the chosen batch size. Now the batch size was taken to be 64 in this case study. Okay, so we can see here the results of the macro F1 results for the first case study. Okay, so the results for the case study 2, the second case study, or the transfer learning case study if you want. Now the macro F1 score for the second case study came about 0.58 with an accuracy of about 0.51. So this is the accuracy, and that's the macro F1 score for the case study 2. The confusion metrics here can show also further these classification results. We can realize that we can see that there is a relatively big number of false positives and big number of false negatives as well in this classification task. The patch size for the second case study is chosen to be 32, right? Okay. Now discussion and further work. As we said, it's continuous work. So the study shows some good results, but further work is still encouraged. The further work can continue in the following paths. Other paths can also be tried as well. So path number 1, different types of transfer learning modules can be used. In the case study 2 here, we used VGG16 transfer learning as a transfer learning module, and was used, but other modules can also be implemented, especially if the modules have been pre-trained on similar images and for similar tasks, right? So if that happens, then it's more likely that this transfer learning would give or yield better results. That's the first path of improving the work or doing further work. Path number 2, more layers can be added to the CNN modules with different optimizers, different patch size and other parameters, right? So more tuning can be done on the module, more complexity can be given to the convolution neural network module that was built in here. Different optimizers, the batch size, learning rate can all be tried and checked to see if one can get better quantitative results for this task. Path 3 of further work can be with regard to applying different processes on images before starting modeling. That could improve the results as well. Processes such as cropping the images, for example. So you could be doing cropping of the CT images. You consult doctors and you realize that there's one that could focus, that cropping the images could focus the work on the infected area or the area that really matters in the images. That for sure can save running time, as well as probably giving some better results or better quantitative results. Okay, so these are the 3 paths that one can follow for further work. Acknowledgement. The authors here would like to thank Izmir Democracy University, where this work was conducted through 1 semester. The authors will also acknowledge the work of the medical staff and others who were referenced in this work as they required. And they worked really hard to manually annotating those images and sharing them in a relatively big data set. And these are some of the other references that one can refer to or that help to build these modules. Very much that's it. Thank you very much.